I'm standing in between you and your lunch. So, actually, lunch is over there. So. So what we were saying earlier, Pavlo, was in his talk said Erlang fits certain types of problem. We just saw, what a brilliant, payment gateway has been developed now in Erlang, and how certain parts will also be migrated to Erlang. And if you think of it, think of the types of problems we've been looking at least server-side problems. But this very much can relate also to embedded. So, first of all, what is scalability? Scalability is the ability to handle traffic spikes, to behave predictably under extended heavy load. The summer platform, gets to Christmas, everyone's using it. They're giving, Foursquare bang for the buck to start getting into the US market. It needs to behave predictably. You need to know how it behaves. And it needs to carry the traffic it was designed to handle. You need to write a system which is, massively concurrent. So you've got millions of simultaneous requests being handled. So these are requests which are all running independently of each other. Once again, take payments. A payment you're doing shouldn't interfere a payment someone else is doing. Think of SMS TV voting, where it's all very quiet. They say don't vote, so people start voting, and then all of a sudden, vote now, you'll get a huge spike. You need to make sure that you handle all of these SMSs and you handle them individually. High availability. What is high availability? Now, high availability is no single point of failure. If you go in and you ask Joe Armstrong, one of the co-inventors of Erlang, he'll say you need at least 2 computers. Leslie Lamport will tell you 3. But it's not just computers. You need redundant networks. You need to make sure that, even if the sysadmin trips over the network cable, your system will continue running. You need, in the case of, the example we saw earlier where you've got a base station running under a palm tree out in the middle of the jungle, you need battery backups, you need generators, you need to cater for hardware failures. Usually, had we had a bit more time over, there were some really interesting stories I could have told you over hardware failures, which were handled. And you need to distribute your software, and that's relatively easy. Much harder is distributing your data. And, software is important, but it's not just about software. Full tolerance. Your payment gateway needs to be full tolerant. So even if things start going wrong, your system needs to continue working. If there are bugs, there are crashes, payments still have to go through. And full tolerance is all about the ability to isolate an error, regain control, and continue operating despite things are going wrong. So limiting the scope of the error. And with all of this, this is an Erlang conference after all. And what will we say? Well, use Erlang, of course. It's simplicity in your design. It's makes life much easier. It's got built-in distribution. It's got software upgrade. But that's not what I'm going to speak about, because if you go in and need to write a massively concurrent soft real-time system, a system which never ever goes down, a system with built-in distribution which manages millions of simultaneous requests, you need more than just a programming language. A programming language will get you just so far. You can go in and you can complain about curly brackets or weird syntax, but at the end of the day, it's just a language. And you need much, much more if you're developing really complex systems. If you think of it, a lot of the problems payment gateways solve are the same problems telecom systems solve. They're the same problems embedded software in cars will solve. And what happens is you don't want to go in and reinvent the wheel. You don't want to go in and redevelop the same monitoring tools time after time, the same deployment tools time after time. And this is where OTP comes in. Now, Ericsson, when they were working with Erlang very, very early on, realized the need for the OTP middleware. And we've had some examples of what OTP is about. We've spoken a bit about release handling, We've spoken a bit about generic servers and finite state machines, but in fact it's much, much more than that. Now, Ericsson realized this very, very early on, and as early as 1993, when they started working on the very first commercial project, which was the mobility server, the ability with DECT phone to roam from one network to another. They had a project called BOS, the Basic Operating System, in parallel, which was the predecessor of OTP. It was merged with OTP in the mid-90s, and to create what is part of the Erlang release today. And if you think of it, Erlang per se is just 33% of the power you get from using the stack. The other 33% is the virtual machine. It's the way they've implemented the scheduler, the garbage collection mechanisms. And the last 33% is OTP itself. Now, how many of you here are here to learn a bit more about Erlang? Okay. So, do you know what OTP means? So you could mean on the phone, or has been suggesting one true pair, or oh, this is perfect, has another suggestion. Unfortunately, it's none of the above. What it means is, well, what it stands for is the Open Telecom Platform. Very, very unfortunate name for what it actually does. The very, very first consultancy gig I had outside of Ericsson, and this was back in 2000, I went in and it was my first code review with a company who had picked up Erlang as open source, and I was giving them feedback. My first reaction was, why aren't you using OTP? And the response was, oh, we're doing instant messaging servers, we're not doing telecom. The history of OTP, well, the name OTP comes, O stands for openness, and the term OTP was coined within Ericsson by Ericsson management in the mid-90s. In the mid-90s, the Ministry of Propaganda at Ericsson believed, that they had to push out the message of openness. It was before the Berlin Wall fell. No, right after, but they believed openness was important. You'd walk down the corridors at Ericsson and you'd see posters of open fields. No one in management could really tell you what open meant, but it was a buzzword, and you had to be buzzword compliant, so they thought it was really, really good. Today, well, we talk about openness referring to the openness towards other programming language. The ability, JSON, XML, SNMP, Java, C, and using Erlang as a glue. At least, that's the explanation we try to give. Telecom, well, absolutely nothing to do with telecom. Yes, you download Erlang, you might get the diameter stack, and you might get the Megaco stack, but these are just standalone separate applications which in fact shouldn't be part of the OTP release. Telecom, OTP has nothing to do with telecom. What it is, well, we refer to telecom system as distributed, massively concurrent, soft real-time with requirements on scalability and high availability. And usually, that's what the telecom refers to. And platform, indeed, the platform is the true thing which OTP is. It is a platform, it is middleware to help you solve the problem. Now, what is the middleware itself? See middleware as a set of abstract principles and design rules. So, the references we've heard about of OTP so far have included release handling, they've included upgrades, they've included generic servers, but it's much more than that. What OTP tells you is how to go in and design your Erlang system, how you glue your components together into what we call a release, and then how you then distribute and manage these releases. So, in effect, they'll describe the software architecture of your Erlang system, and you need to follow these principles to make sure that all of the existing tools which come as part of Erlang OTP distribution are all compatible with them. Very, very important is that it will facilitate the understanding of systems among groups. So if someone who's been using OTP needs to go in and understand someone else's code, they won't spend time understanding the generics parts, the parts which are similar from one system to another. All they have to do is focus on the specifics. Now, and I'm talking about the specifics of systems. Systems will do very, very different things, but the issues they need to resolve are always the same. And there are the fault tolerance layers, you need to deploy and upgrade the systems, and that's what all of these middleware, which comes as part of Erlang, actually resolves. Now, one of the questions, which you were bringing up earlier is, don't start with OTP. No, absolutely not. Don't start with OTP. You want to start with Erlang and start programming in Erlang. It's part of the learning curve. You want to go in and reinvent the wheel. And only once you've invented the wheel yourself will you understand the value of having something which is round and spins. And it's also part of the learning curve as well. And I'm going to give you some examples in my talk. Now, there are a lot of libraries which come as part of OTP. You include, basic applications, so the Erlang runtime system, the compiler, the standard library. You've got a lot of operation and maintenance applications which are already built in. So you've got the standard MIB, the operating system monitor. You've got SNMP. You've got other MIBs, standardized MIBs as well. You've got interface and communications towards other programming languages and environments, TCP, UDP, Corba, ASN1, crypto, interfaces towards other graphical applications as well. And, quite a few tools as well. You've got tools for release. Now, release tools are, you've got tools for testing. I'll come back to the release tools in a second, but you've got tools for testing, so they come with eUnit and Common Test. eUnit relatively lightweight, Common Test heavy, and it just depends what phase of your software development you're in. eUnit is good for unit testing. Common Test is good for system testing. You've got mocking frameworks. You've got release and upgrade tools. Some people ask, is it worth the hassle to deal with release and upgrade tools? And it completely depends on your circumstances. You've got one instance of the system. There it just depends on how big you are as a company and what level of maturity you've reached as a company. There have been instances where we've come in and people didn't know what versions of modules they were running in production. They'll go in, people will deploy systems, these systems will never go down, they're fault tolerant, they'll heal themselves when something does go wrong. And then 4 years later, when something does really go wrong, what's in the live system and what's in the code repository are completely different. No one has a clue. And that's really where all of the release handling, which comes with OTP, comes into the picture. And yes, it is cumbersome, but what you do is you tend to automate a lot of it. The release handling was never completed because they started working on it and they came to a certain level. And at that point, the person who was working on the release handle actually left Ericsson and became one of the co-founders of Bluetail, the first Erlang startup, which Nortel acquired back in 2000. And so what happens there is that the release handler on its own is pretty useless. Well, it's not useless, but it's bulky, and you need to start using Reba on top of it, and then you start writing your own layers. And if you look at companies which have a lot of systems, they will have automated everything based on all of the release principles which come as part of OTP. There are a lot of tools, low-level debugging tools. You've got DBG. DBG goes in and allows you to turn on the traces on local functions and global functions, trigger trace events and functionality based on your values in your variables, so based on certain parameters or messages or values. And you're able to do that without trace compiling your code, so just with any code in production, and with very, very little overheads. You've got tools for profiling concurrency bottlenecks, for finding concurrency bottlenecks, for profiling your code. You've got the Observer, which is a front end to many other tools. It allows you to look at the states of the system internally, and so on and so on. So there are quite a few debugging tools. People say, well, use Emacs. Well, the reason they say use Emacs is that a lot of these debugging tools are actually integrated in Emacs. And it's just, I think, that's a cultural thing. A lot of Erlang devs originally were Vim users and Emacs users. At the time, Emacs was the most flexible of the editors. So, that almost became the IDE Erlang developers use. And I think there is a big awareness today that with more and more people using Erlang coming from other backgrounds, a lot needs to be done with IDEs and integrating it so that people feel comfortable while doing the transition. Now, OTP itself is part of the Erlang distribution, and at the risk of repeating myself, it's, the advantages of using OTP is that you will use much less code. You reuse a lot of the libraries, a lot of the functionality which is there in your architecture, in your processes. And as a result, you end up producing much less code. I don't know if any of you are aware of the study Harriet Watt did, where they took some C++, Harriet Watt University is a university in Edinburgh, and they took some C++ applications which were in production at Motorola, and they rewrote them to Erlang. I mean, just go in and Google C++ Erlang Motorola comparison, and you'll find quite a few academic papers which were written in that area. And what they discovered was, depending on how you counted, you got 4 to 20 times less code than the C++ counterpart. And the 20 times less code is when you actually included OTP as being part of the Erlang language. And 4 times is if you included OTP, because with C++ you didn't have that type of middleware. Motorola had to go in and implement its own middleware, which it did really well, but they had to do it, and they couldn't just go in and reuse something out of the box. So it's less bugs. It's and you end up having a much more solid tested code base and solid code. I've actually only found one bug in behaviors myself, and it was actually visually reading the code, and that's using behaviors now for the past 15 years. And most of all, I think Erlang developers are known to like beer, and using OTP will give Erlang developers much more free time. The original thought behind it was actually the 9-to-5 programmer. So, programmers in large companies will go in at work, they'll clock in at 9, and they'll start doing the work, they'll start doing a brilliant job, and at 5 they'll clock off and they'll go off and mow the lawns or collect their stamps or go fishing or whatnot and clear their minds. And then this is unlike guru programmers who once they've clocked off work and they're walking home, they're thinking about this complex algorithm. They're thinking, have I actually covered all of the possible error cases? What happens, if this system goes wrong? How will that revert into the system itself? And what OTP tries to do through its behaviors is try to hide a lot of that complexity. Now, OTP behaviors per se, see them as a formalization of design patterns. Now, think of an Erlang process. Erlang processes, once they're doing very different things, they'll share a similar structure. You have to start a process will receive message, it will handle the messages, it will terminate or possibly even crash, it will send replies, and so even if they perform different tasks, they will perform them solving a certain type of pattern or a certain type of problem. And what they've done is they've looked at the most common patterns in OTP and created a framework containing the generic code for each of these patterns. And so what you're getting is actually a library module, which is your generic behavior module. And you've got your process. Your process actually runs in a generic behavior module loop. And what the developers need to do is write their own specific callback module. And it's in the callback module where all of the specifics of what's being done are put in. So if you think of a generic behavior module, that's where you'll start your system, that's where you'll start your process, that's where you'll stop it, that's where you'll handle termination, and that's where you'll store your state, that's where you trigger off your software upgrade, that's when you send messages and receive them. In the specific callback module knows nothing about the generic behavior module. And all it does is it exports a set of callback functions which handle the very specific code of what you're doing. So in the case of SumUp, you'd have a call to handle payment, a call where you reserve the funds, a call for recredits, and so on. And each one would be as a callback function, which would, when done, return everything back, return control to the behavior module itself. And the behaviors they found include things such as generic servers. So the whole client-server behavior, I think that's a behavior of all behaviors. All other behaviors are actually a variant of the generic server. There are finite state machines, so generic FSMs. If you think of finite state machines, what is generic with finite state machines include starting the FSM, stopping it, receiving the events, and state transitions. What is specific are the events themselves and the states you're actually in, and what your next state is once you've actually done whatever it is you need to do. Now, we've got event handlers. Event handlers are there to handle different types of events. So you receive a request, you go in and you handle it, you do something with it, and once you're done, you send back a value. And you can do that, and you can do, for the same event, you have different handlers. So assume you receive an SMS, and for that SMS, what you want to do is you want to log it, you want to parse it, and figure out who someone is voting for in your favorite TV program, and you want to forward it on and store it in a database. These would be 3 different handlers. The event would be the SMS coming in, and then these 3 handlers would be called in succession. And then further, you've got a supervisor. And I'll give you an example of a supervisor later on. But all supervisors do is go in and monitor their processes. And they're very, very simple error handling mechanisms in Erlang, which I'll show you in a minute. And supervisors will go in and they'll monitor processes. That's all they do. And when a process terminates, they'll go in and make a decision over how to handle that termination. So it could be, they could decide to terminate all of the children and restart them. They could decide to go in and restart a particular child, or not do anything at all. And in turn, they could escalate the problem. So they realize that, after having restarted a child many times, that they're actually not resolving the problem by restarting it. So they could decide to terminate themselves. And so supervisors, and then finally we've got applications. An application is just a way of encapsulating everything. So let me give you some examples of what your typical maybe 9-to-5 programmer might not resolve or think of from day one. So we've got 2 processes. We've got a client and we've got a server. Now, if a client sends a message to the server, and it's a format, it's a tuple of the format request, so this is just a tag, the process identifier of the client itself, and the message. This message is received by the server. The server then goes in, handles that message, it could be a payment, and then sends back a reply to the client. So it sends back a tuple with the tag reply and the reply itself. So the reply could be payment accepted or payment rejected. And the client receives the message and says, okay, sorry, your payment was rejected or accepted. But there's a slight problem with this code. Can anyone spot it? What happens if we've got another server? And this other server goes in and sends a message of the format reply, comma reply, so a message of the exact same format to that client. It's not necessarily malicious. It could just be a bug in your system, which happens once every 3 years because of a race condition. The client receives the message from server 2, believing it's a response from this server, and starts giving the wrong reply back to the client. I know we were working on a system, the bug wasn't ours, but it was an instant messaging system, and all of a sudden in the chat boards, external chat boards, you started seeing messages, actually in German, saying, hey, we received someone else's instant message, who's receiving mine? Is the system safe? And something similar was happening right there, where, as a result of race condition, people were getting each other's messages. Now, this was not a problem in our code or in Erlang. It was actually in the load balancers. But it did take quite a while to reproduce it and trace it. So, obviously, what we need to do here is, whenever a client sends a message to a server, we need to create a unique identifier. And that's what we're doing right here. This is a built-in function called makeref, and returns a unique identifier known only within the scope of this function. We send that unique identifier to the server. The server receives it, it handles its message, and it handles the message and sends back a response. And the response we send back includes that reference. This reference is already bound, so we will only receive this message if the second element in that message is the reference we sent to the original client. So that will result, and ref is unique-ish, so I think it will take a couple hundred years before the same reference is reused. So this will guarantee you that the reply you're actually receiving is the reply you're expecting and not another process sending you a message. Everyone following me? So this is one of the many things OTP takes care of behind the scenes. Another one is the following. Think about PID A sending a message to PID B, and PID A now starts waiting for a response, but PID B crashes. PID A is waiting and waiting and waiting, and poor Gustav is there with his demoing his payment system, and it's demoing it, and it's coming through now, and nothing happens. This is another very typical problem programmers don't think about. And what we want to know is that something has gone wrong with the server. And if something has gone wrong with the server, we're transacting a payment, we want to make sure that when we retry, we say, hey, we first check if that payment's gone through or not. And if it hasn't gone through, only then do we go in and retry it. And so what does OTP hide behind the scenes? What do we get in the generic behavior module? Well, we've got, apologies. So what we do here now is we start monitoring the remote process. Sorry. Okay, what's happening? Supervisors restarting, that's right. So what we start doing now is we start monitoring the remote process. A monitor is very similar to a link, and what you do is you start monitoring a process, and if something happens to that process, we get a down message. We get back a unique reference, so all of a sudden we don't need to make a ref anymore. We just use this unique reference in our message and expect it back in the reply. And if we don't get a reply and something happens with the remote node, the message goes down. We receive a down message telling us that the process terminated for this particular reason, and we can go back and say error, there is no process, error no proc on the remote part side. So hopefully you'll have an intelligent client at SumUp which realizes something has gone wrong with a server. Let me wait a little while, a random amount of time, and then retry. First check how the transaction went. Maybe the transaction did go through, and then the server crashed before sending back a response. Maybe the transaction didn't go through at all. So you go in, you check, and you execute a new payment. And so what happens here is, we send back a message, we get a reply. Now, all of a sudden we get a down message. Have you seen what's happened here? Have you seen the sequence? This is another catch which you can get. So you go in, you send a message. No, that's not it again. So you go in, you send a message, okay, and your process crashes. We get a down message. Fine. You go in, you send a message. So we're monitoring process B. When you're monitoring process B, you get back a response, but before PID A is able to retrieve the response, the process crashes, PID B crashes, and also sends us a down message. So this is before we actually go in and start demonitoring the process. So what we need to do in our reply here is when we receive a reply, we say we want to demonitor the process, but to make sure that the down message isn't kind of garbage collected, isn't stuck in our mailbox and never read, and it won't ever be read because we're pattern matching on a unique reference. So to ensure we don't get any memory leaks, when we go in and demonitor the remote process after the call, we also need to go in and flush any down messages we might have received after the call. So these are just some of the tricky things which can happen with concurrency behind the scenes. And OTP, takes care of all of this for you. Other things it takes care of includes bottlenecks. It will include there's to a certain extent race conditions and the deadlocks as well. Now, something which people will tell you about Erlang is to fail safe and fail early. And that usually gives goosebumps to C programmers saying, I can't make my code crash. But what you want to do is you want to go in and isolate your error. And you can do that in Erlang because you've isolated your error in a process. And once again, start thinking of the 9-to-5 programmers. They'll go in, they'll start, they need to go in and they need to convert a day, so the atoms Monday through Sunday, to a number, to an integer, to the relevant day of the week. Now, a defensive programmer will go in and say, guess what, if you're passing me an atom, I don't want to crash. If you're passing me something other than a day of the week, I'll return error unknown day. And this is what we refer to as Erlang as defensive programming. You don't want to do that. You actually want to make your code terminate. Now, in a case statement, if you're passing in convert, any other day, and it doesn't match any of these, your process will terminate. And that's really what you want to do. You want to isolate error and make that process terminate, not try to handle it. If you were actually going in and handling it, for every time you call convert day, you would actually have to check, are we returning error unknown day? And if we are, what are we going to do about it? The data in our system is corrupt. And I've actually seen so many more bugs being inserted in systems because of defensive programming than the issues they're actually trying to resolve. And so what you do in Erlang is you isolate error. You make your process crash. I actually shouldn't be using the word crash because, well, there are a few embedded programmers here getting goosebumps. But make your process terminate, I think, is the politically correct word. There is no shared memory. And what you do if your process is critical is you let a supervisor restart it. And when the supervisor restarts it, you go in and create a state. So for those of you who have dabbled a little bit in Erlang, you'll know that you've got processes which are all linked together. And if a process terminates, an exit signal will be sent to the process trapping exits. We denote processes trapping exits with 2 rings. So this process here will know that process A has terminated, and it can then go in and decide what to do with that process. So PID B usually goes in and, decide, if it's an important server, if it's an important behavior, it will restart it. If it's an SMS going through the system or a payment, it will most probably not restart it, because it's probably going to be a bug which will be persistent. And you'll end up getting a cyclic bug. So what we've done in Erlang is, in this case, we're restarting it. And what we've done in Erlang is we've taken a process trapping exits. We've added a bit more logic behind the scenes. We're adding many more generic kind of error cases which can handle. And we group it, use this process called a supervisor to create what we call a supervision tree. And a supervision tree, a supervisor will go in and monitor processes or behaviors and other supervisors, giving you a complete tree itself. What you usually do is you tend to group logically connected processes under a particular subset of the supervision tree. And on top of the supervisor, we've got the workers. And what we do is we package all of this into what we call an application. And an application is your Lego brick in an Erlang system. It is your building block. And it's a logical unit of processes and modules grouped together which will perform a certain task. And you'll start them as a whole, you'll stop them as a whole, and usually, it contains libraries but also supervision trees. And your Erlang system is nothing other than a group of loosely coupled applications. So, in this example, we've got the Erlang runtime system, the kernel, the system architecture support library, media database, and so on. And all of these, together with open source applications for logging and for metrics, together with whatever it is you're doing, could be your card payment systems. So, a complete Erlang system is built as a release. So whether you like it or not, it's very hard to get away from it. Conclusions is, yes, use Erlang, but don't just use Erlang, use OTP. once you've used Erlang, once you've done these mistakes, you'll go in and you start learning actually the benefits of what OTP as a whole framework and as a middleware actually brings to you. There's a slightly steeper learning curve, but the documentation for it has gotten much, much better compared to when I first, got told that we're not doing telecom systems. There are books, I would recommend OTP in Action. There is a book, a lot of it is included in Learn You Some Erlang for great good. And I'm actually writing a book now together with Robert Verding and Simon Thompson also on OTP itself. It will be ready when it will be ready, but yeah. Any questions or any thoughts? Yes.
What's the difference between links and monitors?
So a link is bidirectional. So if I link to you, if I terminate, you receive the exit signal, you terminate, I receive the exit signal. A monitor, if I monitor you, you don't know anything about me if I terminate. And in effect, a link is in fact two monitors. And it's, I'd say, design flaw in the language when they invented it to believe links were enough, but in fact they should have just had monitors. Yes?
It was the topic of defensive programming.
Yes.
I noticed that I ended up adding a lot of defensive programming afterwards for user-facing code because I kind of to tell them what went wrong. Absolutely.
So what I'm saying, when I say don't be defensive, trust the data which is within your system. But do not trust data coming from the outside. You need to make sure that any data coming into your system works and is correct. So use your data absolutely. Go in, parse it, check it, make sure it's exactly what you want and provide the best possible feedback. And if it is correct, then allow it into your Erlang system. Okay. But once it is in your system, trust it.
Makes sense.
Yeah. Okay. Lunch, I think. Thank you.